All right. Well, welcome and thank you everyone for joining this webinar on climate change impacts on water supply and quality. My name is Chloe Shields. I'm the Deputy Director at the New England Environmental Finance Center. I'm joined by my colleagues Martha Shields and Courtney Crossgrove. And we're based at the University of Southern Maine in Portland, and we work across New England to help build local capacity to fund and finance environmental and climate priorities. We've organized this webinar in collaboration with our partners at the Kennebec Estuary Land Trust and the Casco Bay Estuary Partnership. And we've got Josie and Ruth in the audience from these organizations. The reason for the webinar is because the New England EFC, CBEP, and CELT are currently working with the towns of Arousic, Georgetown, Phippsburg, Woolwich, and Westport Island as part of the Governor's Community Resilience Partnership that you see described on this slide. We're about halfway through this 6-month project where we're working with representatives from each of these 5 towns to understand the local impacts of climate change and what each town can do to prepare and adapt, both individually and also as a regional group of neighboring towns. And then we will work with each one of them to help them apply for grant funding from the governor's office to implement a project of their choosing. So as we started exploring different climate-related issues in these communities, one area where town representatives, many of whom are on the webinar today, were interested in learning more about was water supply and quality. And as I'm sure a lot of you know from residing in these areas, in these rocky coastal towns, the water supply comes from groundwater via private wells. And the aquifers that feed these wells are made up of bedrock fractures that are recharged from precipitation. So we heard from the town representatives we've been working with that there are growing concerns about the already limited rate of recharge and the potential for saltwater intrusion or other impacts of climate change. So we've assembled some expert speakers on this topic, and now I will hand it over to my colleague Courtney to get us started. Thanks.
Thanks, Chloe. So I just want to go over a few basic norms for this meeting or webinar. We are recording it just in case some of the members of the towns would like to watch it later on or couldn't make it. Throughout this webinar, please keep your mic off throughout the presentation. That way we can hear the presenters clearly. If you have any questions, please add them to the chat. We will be monitoring the chat, and after the 2 presentations, we'll go through all those questions with the presenters, and we'll just be monitoring that and keeping track of it. A brief agenda for the day. We're going to start off with Ryan Gordon from the Maine Geological Survey. He's going to go over some basics about the topic, and then we're going to transition to a group from New Hampshire who have done some work, some kind of case study work on this. We have Jane Knott, Kyle Pimentel, and Jennifer Jacobs. And then, as I said, we'll follow up with a big Q&A session. Hopefully we'll get to all of your questions. And we have 20 minutes allotted for that. So again, please put your questions in the chat, and I'm going to pass it right over to Ryan Gordon, and I'm going to stop sharing so he can dive right in.
Thank you very much. Let me see if I can get my slides shared here. Okay, you're probably seeing the wrong settings here.
That looks great, Ryan. I think we're seeing the presenter or now we're seeing the presenter mode. Sorry, there we go.
All right, so is it back to the correct view there?
Yep, looks good.
Great. Okay, well, thank you for inviting me. And thanks for the introduction. My name's Ryan Gordon, and I am a hydrogeologist at the Maine Geological Survey. So that's part of the Department of Agriculture, Conservation, and Forestry. And I've been working on sea level rise and saltwater intrusion issues for quite some time, pretty much since I started in 2015 in this position. So I will be going over just a few basics about saltwater and freshwater on the coast and climate change in Maine's hydrologic cycle, and then talk briefly about a case study on Monhegan Island. So the topics I'll go through are first climate change and its effects on Maine's hydrologic cycle, and then kind of dive into what's unique about aquifers when they're on the coast and when they're in contact with salt water or close to it, and then talk about that case study on Monhegan Island. So the hydrologic cycle at its very most basic begins with precipitation. So I don't think that's surprising to anybody, but the source of all of water in Maine is rain and snow that falls on the landscape right here in Maine. So unlike some places in the United States, like Nebraska or California, we don't have fossil water in large aquifers. And we also don't get our water from faraway places, like the White Mountains. It's mostly local precipitation that you're drawing out of a well if you use a well for your water resources. So how much precipitation do we get? On average, the state of Maine gets 45 inches per year of rain and snow, which is pretty generous compared to some places in the United States. So these color-coded maps are just the average precipitation over the last 30 years. You can see Maine is on the wetter side of things, especially compared to the Western United States. Diving into the actual state, I don't know, can folks see my mouse here? I just wanted to know for the rest of the presentation. Okay, thanks. So in Maine, our precipitation does range fairly widely from less than 40 inches up around Caribou and Presque Isle to over 60 inches on parts of the coast and in the mountains. So it's a fair amount of precipitation. Not all of this is going to recharge groundwater resources, though. On average, about half of this precipitation runs off into streams and rivers and eventually the ocean. And about 15% is available to recharge aquifers. The other 35% is evaporated or transpirated through plants and vegetation. Now, I said that this is an average, so the 15% that gets into aquifers on average, it's going to be a lot less than that on like rocky islands or bluffs or clay areas. So that it can be down to 1 or 2% in some types of land cover. So that's just briefly the hydrologic cycle part of it. And now to talk about how climate change and how that affects the water cycle. So the first thing that shouldn't be surprising to anybody who's been paying attention to the greenhouse effect and climate change is that temperatures have been increasing in Maine over the last 100 years or more. So on the top right here, we're seeing a plot of temperatures on average over the last 120 years or so, 125 years, where we've seen an increase already of more than 3 degrees Fahrenheit. And then on the lower right is a prediction for the 21st century. So, approximately 100 years from now, how temperatures might change. And it's broken up into regions of Maine: coastal, southern, and northern. And it's also broken up by seasons. So we can see that in the winter, for example, the predicted increase in temperature is the greatest, while it's the least during the summertime. And we've already seen this with decreasing number of very cold nights in the wintertime, while we haven't seen a huge number of or really a statistical increase in the number of very hot days. The ways that this can really impact the hydrologic cycle is that we have longer growing seasons, so that evaporation and transpiration through plants is greater, and it dries out the soil more. And we have less winter snow storage, so that the snow tends to melt throughout the winter more often rather than really being built up into the spring to the beginning of the growing season. We have earlier spring ice outs and earlier spring river flows, so that the high flows are coming earlier in the year. And we're also seeing more runoff events during winter time, which has a lot of negative effects, among them pollution and erosion as well. And also less frozen soil, which adds to the erosion. So then moving on to precipitation, which is the other big change that we have seen and are likely to see more of, is that we have already been seeing more precipitation, and that's predicted to increase also in the future. So it's more precipitation, especially in the fall, winter, and spring, with once again winter being the most highly impacted. So this is on average a greater increase in precipitation, which will lead to higher stream flows, more saturated soils, which leads to larger and more frequent runoff events, and also on average higher groundwater levels. And that's something that we have been seeing in records around the state of Maine and in New England, especially in shallow groundwater wells, where on average water levels are actually higher. But, and this is a big but, we're seeing and are expecting to see much greater variability in time. So that means higher high frequency or high intensity rain events, as well as short-term droughts. So this is just a kind of an overview of observed changes already in very heavy precipitation events, showing that the northeastern United States has seen a large increase, a 71% increase. And I don't know over what time period this is, unfortunately. But you know, and this is expected to continue with more intense events that are spread out more in time. And then drought, although Maine is a generally wet state, and not given to very severe droughts, we have had a lot of short-term droughts recently, and they've affected Maine throughout the 20th century and definitely over the last 10 and 20 years. So these kind of events can really stress agriculture, especially when they're short-term. And then as they become longer-term, drinking water, so water tables and groundwater levels can drop. So that stresses drinking water resources, ecosystems, and can increase fire danger as well. And we're also predicting that the severity of these short-term droughts might increase with higher summer temperatures. So if we do get much higher temperatures, we can have more rapid drying of soil and more of these flash droughts that we've been having in the last couple of years. So it's pretty timely that I checked the US Drought Monitor this morning, because they had released a new map, which is shown here on the right today. And this is showing current drought conditions in the state. So more than half the state is abnormally dry or in moderate drought right now. This moderate drought area has expanded recently. It started off really kind of right along the coast, but it's increased to most of the populated areas of central and southern Maine. So we're currently in a bit of a summer drought, and this is a pattern that we've seen a lot recently, actually. So here are just a smattering of drought monitor maps from summer and fall over the last few years. So I'm obviously picking the driest maps here, but it just kind of shows you how we've been hit with a series of these short-term droughts. So in 2016 and 2017, both of those summers and fall were quite dry, and they really got the worst in October in both of these cases. 2020 was really a statewide, fairly severe drought, with most of the state in severe drought conditions, this orange color. And then 2021 also was a very dry summer with severe drought conditions that kind of moved around the state from the coast to the interior mountains. So this is something that I think we're gonna have to get used to, especially in the summer and fall. Not that it will happen every year, but we are expecting it to happen more often. Okay, and then moving along to the topic that's probably on the forefront of a lot of coastal municipalities' minds is sea level rise. And I think people are pretty familiar with some of the effects of sea level rise, especially when it comes to inundation of infrastructure and coastal properties. But maybe we aren't quite as familiar with how sea level rise can impact the groundwater systems and aquifer systems that are adjacent to the ocean or right on the coast. So I don't think people will be surprised to know that sea level has been rising in Maine. Over the last 100 years, we've seen about 7.5 inches of sea level rise. And this graph is from the Portland tide gauge station. But before I talk more about sea level rise specifically, I kind of want to go back and do a few more basics on how freshwater and saltwater interact with each other on the coast. So I was talking before about the infiltration of precipitation. So fresh water is coming as precipitation on the land surface. and is infiltrating down and to recharge the groundwater system. So most of the water is entering, the fresh water is entering the system at the water table through the land surface, not the water table right here. So that fresh water has kind of a cycle of movement. It goes downwards and then towards the ocean where it's going to eventually discharge. So that's what these arrows are showing. It's the movement of fresh water towards the ocean. Of course, under the ocean, the groundwater in aquifers there has the same salinity as ocean water. So this is salt water here. And somewhere between salt water and fresh water, there's going to be a transition zone where the salinity is increasing over some kind of a gradient. Sometimes it's a very sharp line, and sometimes it can be spread out over many miles. Really depends on kind of the geometry of the coastline and of the interior land. But a couple of features I want to point out is how this transition zone, it doesn't come right up to the coast, but it comes and meets the ocean just a little bit seaward of the coastline. And this kind of focuses fresh groundwater discharge to the coastal areas. So I also just want to point out that the geometries of this saltwater freshwater interface are different in different situations. So in these kind of graphs, we're approximating the transition zone as one zone with two interfaces here between saltwater, the transition, and freshwater in the transition. These are examples from Cape Cod, but they're applicable to a lot of different places. So this is kind of an example on the left of what we were looking at before. If you have a shallow marsh or a bay, you might have a transition zone that's spread out a little bit underneath the shallow bay or marsh. This happens in Maine too. And then a special case that is very important to island communities and also long and narrow peninsulas that kind of act like islands in Maine. Is that when you have a peninsula or an island that's surrounded by salt water, you will get what we call a freshwater lens, or a kind of a small capsule of fresh water that's surrounded by salt water on all sides, including below it. So this is just an example of a freshwater lens where the recharge is coming down through the land surface, and then the freshwater is following these flow lines downwards and outwards. And the transition zone separates the fresh water from the salt water. So in this case, your freshwater groundwater resources are, very precious. And you don't want to go down too deep with your wells, and you don't want to be right on the edge of the coastline with your wells. So a question that might arise looking at these kind of diagrams is, how do we know where that transition zone is, or how do we know how deep it is below a property or a location, or a place where you're trying to drill a well? That might be something really useful when you're deciding on where to put wells or how deep to drill them. So there's a kind of back of the envelope calculation that we can do before you do any fancier computer modeling. And it's based on the Geibin-Hertzberg relation, which has a fancy name, but it's really just a ratio between the density of fresh water and salt water. Salt water is denser than fresh water, which is one of the reasons why the fresh water kind of rides up on top of salt water, and why you get the sloping interface that goes down underneath the land. So because salt water is about 1/40th more dense than fresh water, you end up with this ratio, a 1:40 ratio between Z and H in this diagram. So in this case, H is the height of the water table above sea level, which might only be a few feet if you're very close to the coastline. And then Z is the depth of the saltwater interface below sea level. So if you have 1 foot of freshwater head above sea level in a well, you can expect the saltwater interface to be somewhere around 40 feet below sea level at that location. And like I said, this doesn't take into effect the complexities of groundwater flow, so it's just kind of a first order approximation. So what happens to this kind of a system when you add a pumping well or other kind of disturbance to the water table? So in this diagram, which is a little more complicated than the ones I was showing before, we have two yellow pumping wells here, one closer to the coast and one inland. And one of the things that happens when you pump water out of a freshwater aquifer is the water table gets depressed close to the well. So we call this a cone of depression because it kind of makes a cone shape around the well itself and draws that down. So when we're thinking about what kind of effect will that have on the saltwater interface below the well, we have to remember that 1 to 40 relationship. So the 1 to 40 sounds kind of good, right? If you have 1 foot of freshwater head, you might have 40 feet below it, or if you have 10 feet of freshwater head, your saltwater interface is 400 feet below. But that can come back to bite you when you start drawing the water table down. So if you cause a drop in the water table of 1 foot, or if a drought impacts the water table, it brings it down 1 foot. You could potentially have an increase, a rise in the saltwater interface of 40 feet to match that 1 foot. So in some cases, you might have a well that's been finished in freshwater, but if you pump it hard enough, you might draw in, or there's a danger of drawing in saltwater below it. In this diagram, at least, the well that is farther inland appears to be safer, even though it's deeper, just because the saltwater interface is significantly deeper. Okay, so what happens when you add sea level on top of this kind of thing? So the first thing that's obviously going to happen is the sea level itself will rise. That will inundate a little bit of the coastline. So we have the elevation of the sea coming up, and that'll going to come up over a little bit of the coast. That increases the pressure on the seabed as well. And that change in pressure kind of upsets the relationship between the freshwater table and the transition zone and what's going on at the sea. So the effect of increasing that pressure is to move the transition zone landward, so inland and upward as well. And then that has an effect on the freshwater table. So the freshwater table will rise as well. So you kind of have this cascading effect of changes in the water system. The increase in the water table will be greatest near the coastline and less inland. So one other effect of that is that the gradient, the slope of the water table going towards the ocean will become less. So it becomes a shallower gradient. Okay, just to kind of summarize some of the processes that affect the saltwater interface that we've just mentioned. One is pumping or potentially drought. That can lower the fresh groundwater table and shift the saltwater interface inland. And then sea level rise has additional effects. It can shift the saltwater interface inland as well, but it has the effect of raising the fresh groundwater table. And it can also flood the nearshore area and erode the nearshore area if you get a lot of wave action. So those are all hazards to kind of coastal groundwater systems with sea level rise. I'm just going to skip the next slide because I think that the following speakers will cover it better. But I just briefly wanted to mention that the types of aquifers in Maine, so we kind of have a clear idea what we're talking about. So I'm going back and forth, back to basics here. So there's 2 basic aquifers in Maine, the bedrock aquifer, which is composed of fractured bedrock. And this fractured bedrock underlies all of New England, where water is found in these discrete thin fractures, like shown in this upper picture. And then on top of the bedrock, in some locations, we get these superficial aquifers that are composed of sediment, mostly either transported or laid down by the glacier. It can be sand or gravel or silt or clay. In those cases, water is found in spaces between grains. The mid-coast region of Maine doesn't really have very many of these superficial aquifers, right on the coast especially. So as you're all aware, we're mostly dealing with the bedrock aquifers as a water resource in coastal towns. So I'll really focus on those. But I want to make a point that I always add to these talks is that this kind of a thing does not occur in Maine. So we don't have underground rivers or lakes or big chasms, cave systems, which are commonly called carts. So this isn't what we're talking about when we're talking about groundwater. We are really talking about very small fractures and cracks in the bedrock, like in these couple pictures. So it's these fractures in bedrock that really provide both the volume and the connectivity for groundwater to flow through the rock. And I just want to point out the frequency of fractures decreases with depth. So about 60% of the Maine coast is rocky bluff, as I was saying. But I also want to point out that about 2% is sand, beach, or dune, which is kind of, it's coveted real estate, it's highly used, and so it's a very important area. Those kind of areas are tapped. A lot of homeowners that are on sandy dune aquifers use these shallow driven point wells, like you can see on the upper right here. So they often have like a little pump house here This pump house has a shallow well in it that's supplying this house up here. This photo is from Honeywell Beach in Phippsburg. Honeywell Beach is really close to Popham Beach State Park. So this was one case study that I worked on a couple of years ago where we were doing a groundwater model for flow in sand dune aquifers, specifically at the beach, at the state park, at Popham Beach State Park area here, but also looking at some of the effects up on Honeywell Beach, which is where that previous photo was taken up on the upper right here. So I don't have time to go into that case study, but it's kind of a talk unto itself, which is pretty interesting. So I just want to quickly move on to kind of describe this case study that was done on Monhegan Island. I wasn't the one who did most of this. It was mostly done by a consultant working for the plantation, Monhegan Plantation out there. But it was funded through a Coastal Communities Grant Program, which is done every year through the Maine Coastal Program. And they were looking at three things, really. They were doing a computer model of saltwater intrusion on their existing well field, and then characterizing the bedrock and looking at the feasibility for installing a new water supply using bedrock wells. So if anybody's been out to Monhegan, it's a very unique place. And they have a unique water system to go along with it. So they have this, what they call a meadow in the middle of their downtown area, which is really a peat bog. And they have these shallow well points there, and they draw water there, store it in tanks, and provide it to the town seasonally, so only in the summertime. So they're worried about saltwater intrusion in that aquifer, and they really are looking for a better and more permanent water supply. So those three components, I'll just go through quickly because I want to give time to the other folks here. But they did a predictive model of saltwater intrusion in that aquifer. They basically found that as sea level increases over time, so they looked at 2020, 2050, and 2080, a rise of 1 foot and then 3 feet of sea level. They saw that the gradient decreases towards the ocean, and the area of contribution to the wells does get closer to the ocean, but it's not really going to draw in seawater, at least under 3 feet of sea level rise. So we might get worse than that. So kind of moving on to the bedrock aquifer characterization. They went around and sampled all of these wells. They're mostly private wells. So the aquifer well points supply some seasonal businesses and the hotels in the summer, but many private homes and businesses also have their own bedrock wells that are generally low yield. So they went around and tested these, looking at chloride levels and elevations. And they found that all the wells were fresh and potable water, but that the wells closest to the center of the island and at the highest elevations had lowest chloride. So then they kind of went scoping out to look for a good place to put a bedrock well to supply the town with water. They did a fracture characterization looking at kind of predominant directions of fractures and lineaments, which are kind of long features in the bedrock that might indicate a fracture area, someplace where you could put a well with greater yield. And then they also looked at potential contamination and just land ownership, how easy it would be to acquire an area free from contamination and put a well in. So they identified a number of different places. In the middle of the island, this is kind of a hill. They have their power station up there, which unfortunately is powered by diesel fuel. So they have fuel storage tanks, which were kind of a source of contamination. But they identified 4 different potential well locations with different pluses and minuses, and kind of settled on this one right here. They were really looking for a place that was far from the ocean and kind of in the middle of the island and far away from contaminant sources. So I think the report, which I could hand out to other folks or getting in contact with Monhegan Plantation, they would do that. But I think the report and the study that they did out here was really good and is a good template maybe for other towns near the coast that are looking at investigating different water supplies or additional water supplies. So I'm sorry I went a little over, but it was a lot to go through. Any questions now, or should we wait until the end of everyone?
I think we're gonna wait till the end. So
Okay,
thank you so
great.
much. This was great. And yeah, if you do have any questions, please add them to the chat and we'll be monitoring that and do the same for the next presenters, and we'll be sure to get to those at the end. And I'm going to pass it right over to Jane Knott.
Okay, well, thank you very much, Courtney. And can everyone hear me? All right.
I can hear you. Yep.
Okay, great. Let's just move this up. Ryan, thank you very much for that presentation. That was great, and it was great to have that all the basics. Preceding our presentation, it was a really nice overview of groundwater and saltwater intrusion, and it was great. I was glad to hear that. So this presentation is climate change impacts on drinking water in coastal communities. It's not necessarily just drinking water. We'll be talking about other things. But we did a study, and when I say we, it's Jennifer Jacobs, who's a professor at the University of New Hampshire. I believe she's on the call as well. And Kyle, you'll meet him in a second. He'll be presenting as well. He's from the Trent Stratford Regional Planning Commission. And basically what we've done is we've done a groundwater modeling study, or a number of studies in coastal New Hampshire. So the question here is, how can climate change affect coastal communities? You've heard a little bit about that with changing recharge and precipitation, drought. We're going to focus here in the beginning on groundwater rise caused by sea level rise. You heard a little bit about that as well. And the effects of that, which is premature subsurface infrastructure failure, water quality degradation, wetland expansion and transition, and sometimes drowning, and the reduced aquifer recharge due to increasing temperatures and evapotranspiration. So coastal groundwater rise caused by sea level rise. Basically, this is a map showing where your communities are located in Maine, and where our study area is located in along the New Hampshire seacoast. So we're not that far away. The geology is quite similar. And here's a zoomed in version. So New Hampshire seacoast on the left, and the Maine communities on the right. And what I'd like you to see here, if you can see my cursor, let me see if I can make this a laser. Yeah, so what's interesting here is in your communities here around Westport Island, you've got saltwater in between land masses. And Ryan spoke about that. You have islands with saltwater on both sides here. And we found that down here in the New Hampshire seacoast, in the northern part of the seacoast with Great Bay, which is a tidal water body, and then the Gulf of Maine out here to the east. So similar situations. I would say the Maine communities, you have a lot more of the influence of the seawater much further inland. So we did a three-dimensional groundwater model. Actually, the first model that was done was a USGS model that was done by Thomas Mack, and it was built in order to look at drinking water supplies in coastal New Hampshire. And we updated this model and used it to look at the effect of sea level rise on groundwater levels in the coastal area. And so what you're seeing here, this is coastal New Hampshire. This is Great Bay that I was showing you before. The colors here, the dark blue is surface water with 6.6 feet of sea level rise, so a lot of sea level rise. This is the surface water effects of the sea level rise. And then the other colors, the red, the orange, the yellow, the light green, and the light blue is groundwater rise beneath the ground surface. This doesn't mean that groundwater is is flooding the ground surface. It's just showing areas underneath the ground where the groundwater level or the water table is increasing due to the sea level rise. And what you can see here is that the effect of sea level rise on groundwater occurs much further inland than the surface water flooding effects that you hear a lot about when you hear about sea level rise. So the groundwater rise signal really is 2.5 to 3 miles inland, whereas the tidal surface water flooding is about 1 mile inland. And this is, of course, affected by geology, the coastal geometry, groundwater pumping, and in some areas you can get groundwater inundation in areas where, near wetlands can expand. But what's interesting here is that the largest effect of the largest signal really of groundwater rise is in areas where the land is surrounded by tidal water bodies on 3 sides, which is very similar to what you have in Maine. So again, this is the study area. This is coastal New Hampshire, and the first model that we did encompassed these communities. And we did this study, and these are the model results that I just showed you. We basically did this study to see the effect of rising groundwater on road infrastructure, coastal road infrastructure. And when we presented the results of our modeling, some of the other communities said, gee, we'd like to look at that as well. And so they asked us to take a look at Newmarket was the first community to say, yeah, do our community. And then Durham said, yeah, we like this work. We'd like to have it done in our community as well. So we did Newmarket, and in Newmarket we did a saltwater intrusion model as well as a groundwater rise model, groundwater flow model, which was different from this model. We did not do saltwater intrusion, but we did saltwater intrusion here for Newmarket, and we did saltwater intrusion for Durham. And this is Great Bay here, and it shows you some of the results. So the results, groundwater rise is shown with the colors over here, and you can see it over in these communities as well. It doesn't go as far inland in these communities because these communities are not surrounded by the tidal water body like this area here. We're now just about to get a contract to do the other communities in coastal New Hampshire. We're basically going to expand the model from Durham north to Madbury, Dover, and Rollingsford. And the Newmarket model, we will expand south to Newfields and Exeter. Portsmouth really wants us to do a deeper dive and do a saltwater intrusion model there, and Newcastle. So these communities are seeing the benefits of this modeling effort, and they're interested in having the whole region essentially done. So why do we care about the effects on groundwater from sea level rise and climate change for that matter? Well, like I said, the first study really looked at roads, and the reason we were interested in doing roads is that as groundwater rises into the underlying layers of pavements, it weakens the pavement structure. And when the underlying layers are weakened because of moisture and groundwater in those underlying layers, you get premature failure of your pavement and premature failure of the road. You can get fatigue cracking, and you can get rutting. So this is a cross-section A to A prime through the Portsmouth Circle. And basically this cross-section is interesting because it shows that when the groundwater is deep and it rises, say, a foot or 2 feet, it really doesn't matter. Okay, so it really doesn't affect much. But when the groundwater is shallow, already close to the surface, and the groundwater rises because of sea level rise, you can get inundation, you can get flooding of roads, you can get damage to the roads, you can get damage to underground infrastructure, and you can affect water quality. So the important thing to note here is that when you do a study like this, you not only want to figure out where the groundwater is going to rise and what the magnitude is going to be, but you also want to find out where the groundwater is in the first place. And you focus in on those areas where the groundwater is shallow. So the next reason we care is water quality degradation. And I'm just going to show you some schematic drawings, just basically to give you an idea. Kyle will get into the details of our study in Durham. But basically what we're showing here is you've got the groundwater table, and if the groundwater rises due to sea level rise or due to more precipitation or whatever, over the long term you have septic systems that were designed for a certain water table depth. If any of you have put in a septic system, you know you have to do a perk test, and the community won't permit your septic system if the groundwater is shallow there. So septic systems that have been permitted for a particular groundwater levels can rise and fall with seasons, but on average, they're typically assumed to stay the same over time. If you're getting systematic rising of groundwater due to sea level rise, then you'll be getting septic system failure near the coast. This I'm pointing to with this red arrow pointing to the treatment zone. The treatment zone is where the contaminants move into the sand and gravel or the subsurface and move through the porous media, and that's where the treatment occurs. When the groundwater rises, that treatment zone shrinks. Another possible problem for water quality is hazardous waste disposal areas. Again, same thing. When hazardous waste disposal areas, and I'm not just talking about landfills, I'm talking about places where there have been contaminant spills. Usually when they close a site, the first thing they look at is where is the groundwater. If the contamination is above the groundwater, you might cap it, you might leave it in place. If it's in the groundwater, it's a problem because the groundwater carries the contamination away from the site and possibly to surface water bodies or wells. So again, when you're getting rising groundwater tables, you want to look at your areas of contamination and determine whether the new or the predicted groundwater levels will be mobilizing contaminants. This is Boston, and basically these are flood zones where there are flood risks, and the blue dots are showing hazardous waste sites in Boston. So in this area you see obviously tidal water bodies. Sea level rise will be causing groundwater rise in these areas, and hazardous waste disposal sites can be a problem in the future that may not be a problem now. Wetland expansion, transition, and drowning. This is showing this freshwater lens that Ryan talked about. This is actually a barrier island. You can see the dunes over here. You can see the wetlands in the back, the back area, the inland areas, and as sea level rises, you have the salty groundwater rising, and the fresh groundwater lens is shrinking. And you get flooding. You get some flooding here, which can damage ecosystems and just really change the system completely. So climate change, aquifer recharge, and water supply. I just have one or two slides here. I did a study with the University of Massachusetts in Boston, looking at the effect of climate change on groundwater, not just coastal groundwater, but inland groundwater. And we used some research that was done by the USGS in New Hampshire, and basically they looked at the effect of rising temperatures, increasing evapotranspiration on aquifer recharge. And these are three sites: Portsmouth, New Hampshire, Hampton, New Hampshire, Dracut, Massachusetts, and Pepperell, Mass. And the pattern is the same. It basically shows that in January, February, and March, the recharge is going to decrease significantly. And in the fall months, September, October, November, the recharge will will increase. But overall, over time, the recharge of aquifers will decrease, and that is due to the increasing temperatures, the increasing evapotranspiration, increasing runoff as the storms become more intense, and you get flooding as opposed to the slower recharge that happens over time. Saltwater intrusion from pumping, I won't spend any time on this because Ryan did such a nice job, but when you get increasing temperatures and increasing evapotranspiration in periods of drought, communities will pump more, and when the wells are close to the coast and you're increasing your pumping and sea level is rising, then you will have more saltwater intrusion. And this is just an example in Long Island. Long Island has a lot of public water supply wells for their drinking water all over Long Island, and this barrier island here. This shows that the groundwater is less than 11 feet deep. So they realize that they will be having issues. They're already having issues, and they're trying to deal with that. So conclusions, the groundwater rise zone, which is the zone where groundwater will rise with sea level rise, it extends up to 3 miles inland from the coast and the New Hampshire seacoast with 6 feet of sea level rise. Impacts will occur where groundwater is already close to the surface, and that can be premature pavement failure, it can be infrastructure damage, stormwater underground utilities, sewage treatment plants, water quality degradation of drinking water and surface water bodies and ecosystems, and wetland expansion and groundwater inundation. Groundwater discharge, I didn't mention this, but groundwater discharge to freshwater rivers in the groundwater rise zone will increase, and groundwater discharge to the tidal estuaries will decrease. Saltwater intrusion, it's marginally affected by sea level rise in our study area in New Hampshire, the New Hampshire seacoast, but the inland extent increases with depth. So when you have a deep well, the wedge of saltwater intrusion tends to go farther inland, and so it can affect your deep well, and it's influenced by pumping. Aquifer recharge is projected to decrease with implications for water supply. And that's it for me, and I'm going to hand it off to Kyle. So I will stop my sharing. Thank you very much.
Thanks, Jane. So folks have heard from both Ryan and Jane on sort of the more technical side of things. And so what I'm going to focus on is how practitioners can take this data and apply it at the local level. So as Courtney mentioned, my name is Kyle Pimentel. I'm the Principal Regional Planner at Stratford Regional Planning Commission. And over the last couple of years, I've had the opportunity to work with Jane and Jennifer on some specific work on taking this data and then applying it at the local level. And so I'm going to kind of walk through what we've done in Durham and Newmarket, what we looked at, what came out of that project, the process that we went through, and some potential suggestions for folks in Maine to look into that you might be able to sort of replicate in your community. So to sort of start out, these projects were similar in a lot of ways, but they had slightly different outcomes, and that's for a number of different reasons. The Newmarket project was kicked off somewhere around 2016, and we wrapped that up in 2017. But we had a project budget of only, roughly 20,000, which was broken up between the Planning Commission and then also Jane's work for the modeling. And that was a grant that we received through the Department of Environmental Services, their Source Water Protection Program, which is a program that is really looking to provide funding to municipalities to address any sort of drinking water issues that they might have. On the other side, with Durham, a few years later, we applied for a state revolving loan fund. At the time, it was a new program that was allowing for planning projects to be eligible, and they were having $75,000 worth of principal forgiveness as part of those loans. That was in 2020. I think now they're up to the same program is offering up to 100,000 in principal forgiveness. And so having not only a higher budget, but what we had learned over those years and how the science has changed a little bit provided us a little bit more information with doing things a little bit with things a little bit more clarity in Durham and being able to take a little bit of a deeper dive than what we did. And so one of the first things that we had to do in both communities, and Ryan touched upon this a little bit, was the sort of basic understanding of what this means. A lot of folks in our communities, if you talk about flooding, sea level rise, they understand that the surface water side of things. They've seen it, they know what it looks like, they know how often it happens, when they can anticipate sort of a higher tide from a full moon or a king tide that happens a few times a year. They know what that looks like. They don't necessarily understand what is happening under the ground and what some of the impacts are from sea level rise in terms of groundwater rise. And so that was, something that we had to tackle right away was getting folks to gain that understanding. And one thing that I'll sort of reiterate a few different times is that our communities have been asking for this information. There's been a ton of work on coastal flooding over the last decade or so, but this issue with groundwater rise is relatively new, and I think that it's been something that a lot of communities have really been asking for more information on. The other thing that I mentioned earlier is this sort of ever-changing science and how there are things that are uncertain. A lot of this work is based on models, and those, what feeds into those models will change. For example, the data that we had in 2014, the emission scenarios that we were looking at are somewhat different, even just 5 years later in 2019. In New Hampshire, by statute, we need to provide updated science every 5 years and to sort of track these projections to see where we are, see how close in line we are with what is being predicted for 2050 and beyond. And so, there was a question in the chat as to whether, this model, would work in different conditions. And that's something that, along with changing science and uncertainties, like to take into consideration that, this is not a one size fits all. We have to sort of tailor these things based on the geographic conditions and the data that we have available to us. And in some cases that may change. In terms of how we wanted to structure this framework with working with these communities, we laid this out in a way that was very similar in both Newmarket and Durham. And so the first thing that we put together was a sort of a technical planning committee. And so that was local stakeholders that were involved. In some cases, that was folks from the Public Works Department or Community Services, road agent, engineers, town administrator, the planner in some cases. And so, we wanted that sort of expertise to help guide us along with the project team. And so it was really helpful to sort of get that localized input as we were going through the project and ensuring that there was buy-in at the local level of what we were doing to ensure that, that they were on board and understood what we were doing and eventually what some of the actions were that we were recommending. And so there were different phases to the project. Data collection was sort of the first thing that we did, determining what community assets we wanted to take a look at. And Jane touched upon this In Newmarket, because of the scope of work, it was somewhat limited, where we were kind of looking at drinking water supplies and contaminated sites, but we didn't go too far beyond that. In Durham, we were able to look at a lot more. We looked at not only contaminated sites and private drinking water supplies, we also looked at septic systems, roadways, community assets, stormwater infrastructure, utilities. It was a much larger scope, and we had more time to do a lot more data collection at the local level to kind of look at that. The model construction and the scenarios are really more Jane and Jennifer's level of expertise. What the community was involved with was selecting what sea level rise scenarios to use, so that could be fed into the model. And then what came out of that were GIS shapefiles with not only the groundwater intrusion, but also the groundwater rise extensions of what the groundwater rise and what that might look like. And so what we were able to do is take those shapefiles and overlay them with those community assets and do a very basic sort of intersect analysis to determine where there were going to be or what assets were the most vulnerable. I'll talk a little bit more about exactly how we did it. And then from there, we kind of summarized our findings and did some outreach to the community, presenting this to town council or the board of selectmen, to the planning department, also to a leadership committee, which was made up of, in Durham, which was made up of all the department heads in town, to kind of get the word out there about what we found in some of the recommendations that for them to consider over time. So I'll talk a little bit about Newmarket first, and then I'll get into Durham. So for the Newmarket project, our goals, our overarching goals, were really to have a sort of increased understanding of how sea level rise might impact drinking water sources. This was the first time that the Planning Commission was really getting involved in this work. UNH and Jane and others have been doing some of this modeling, but the Planning Commission at the municipal level in our communities, which the Planning Commission in which I work for, are more inland communities. I don't have any communities that are directly on the coast. That's the Rockingham Planning Commission, which is just far south. And so we didn't have a huge understanding of what this meant and what this impact might be to drinking water supply. So that was one of our top goals, identifying areas which might be vulnerable, and then also to provide a report that would have some adaptation actions for the town to consider to become more resilient. And so I'll kind of just walk through a couple of maps that we created as part of this project. This shows 1 foot of sea level rise by 2030, what the groundwater rise areas might look like. And then if you start to sort of project out and an increase in that sea level rise, what that might look like. So this is 2.7 by 2060, 5.2 by 2090, and then sort of, the highest scenario is 6.6 by 2100. As Jane mentioned, and I think it's really important to note that the ranges of groundwater rise, in this case, in Newmarket, you can see anywhere between 1 and 7 feet, with just within, almost a mile inland of the coast. And so impacts that you will likely see much farther inland than you will from sea level rise and coastal flooding. And so it's a little difficult to see, but where that circle, that purple circle is the one area that is the highest amount, which is that 7 feet of rise. And that's essentially right where the Moody Point development is, in the location of 3 wells that service that development. And so to get to the point that Ryan and Jane were making, that pumping has an effect on this sort of reinforced that notion, is that we saw, in terms of the model, saw the highest levels of groundwater rise in this area where there were 3 wells at varying depths that service that Moody Point development. So in looking at some of the vulnerable infrastructure that was within this area, I already mentioned the 3 wells at Moody Point. It's important to note that those wells already experience high salinity levels. and that they're actually higher than the EPA's standards for secondary taste. What they have to do is the 3 different wells at different depths have to operate in a blending system in order to sort of help address the salinity issue. The other thing that was done by the homeowners association was to limit how much water could be drawn in the summertime. So they were really trying to limit water irrigation for private properties so they could limit the amount of pumping that was done in the summertime. So this area was already experiencing some significant issues prior to this study even being done. There were 2 contaminated sites that were found, 1 sewer pump station, and roughly 30 private wells that were in this area. Jane mentioned that there was also saltwater intrusion, GIS maps that were created. And so again, kind of the area centered around Moody Point was sort of experiencing the highest levels. The deeper the wells have the highest levels. You've already heard that from Jane and Ryan. And that those that are closest to the groundwater table are more vulnerable. The model also predicts in some of these areas an increase anywhere between 8 and 12% in those salinity levels over time. And that's out to the end of the century using the highest sea level rise scenario that we used, which was 6.6 feet. The one thing that we really didn't have a whole lot of data on was septic systems. And so that in general is a challenge for New Hampshire. We don't have a great data set for our municipalities on septic systems. And so what we had to do is we created a map that looked at sort of an environmental risk analysis that was based on surface water features as well as soil conditions to determine what areas would likely be the most vulnerable for a septic system if it was close to one of these areas. And we used any property that had a well on it and wasn't connected to municipal sewer. We made an assumption that there was going to be a septic system on that site. The problem was that we had no idea where on the site that it could be. And so we tried to place some points down that were close to the house, but there was really no other way for us with the limited funding that we had to get more specific than that. And so the big caveat here is for this project, this really should be used as more of a preliminary guide for the community to think about. So the report had 6 planning topics that we tried to cover, some outreach and engagement that we could that the community could do to landowners, looking at some planning and regulatory impacts. I already mentioned the one that the homeowners association took on in terms of limiting some water use restrictions, looking at long-term drinking water solutions, infrastructure and equipment upgrades, some additional research that may need to be done, and then also thinking about it in the context of emergency management. And these actions were developed in conjunction with the Planning Commission and the planning team. Along with the recommendations, there were timeframes and potential funding to kind of help the municipality move forward. One of the things that I wanted to share was that these reports are only as good if they are reviewed and implemented. And so I just wanted to show an example of what Newmarket did do. In 2019, there was a warrant article that was put on the ballot to look specifically at constructing 5,200 feet of a water main to connect Moody Point development to the water system. I happened to see a question earlier about what can landowners do. And so outside of treatment, another option, if possible, is to connect to a municipal system. And so this was a $1.8 million effort that was passed at town meeting in 2019. And so I think right now where they stand is that they are looking at preliminary engineering for construction for this project in the future. But this was just a good example of how that report helped provide the necessary information for decision makers to put this on a warrant and put it in front of the vote. Next, I'll talk about the Durham project. So the goals for this one were expanded a little bit. So
Kyle, can I just interrupt you briefly? Sorry, we are running a bit behind. So if we can do a quick recap of this project and save some time for questions, that would be awesome.
sure. So the Durham project, was looking at, it went beyond just drinking water supplies. And so we looked at a number of different assets. I'll run through these scenarios really quick. We looked at 2 feet, 4, 6, and 8. And so similar to Newmarket, the range was between 1 and 8 feet, but went all the way to about 1.5 miles. The town decided that they were going to use the 6 feet of sea level rise as a scenario. The other thing that we had that we didn't have before was depth to groundwater table. And so what we looked at was areas that were the most shallow, 0 to 5, and we overlaid that with the groundwater rise areas to sort of come up with a modeling result that showed the most vulnerable areas that we were going to kind of concentrate on. We also did a saltwater intrusion map, and we identified some areas for the community to think about there. I won't go through all of this, but these are some of the results of what impacts were to some of these assets and resources. And I'll just really quickly run through these maps. Here's the stormwater assets that were there. We have our municipal facilities, some of the critical facilities, just to highlight these areas of roadway. So that is Route 4 to State Road. It's very heavily trafficked, and there are significant areas where this road is vulnerable. Private infrastructure, so septic and sewer, or septic in wells, contaminated sites, other utilities. I'll just call out a large water main that services Portsmouth, as well as some of the sewer lines leaving the wastewater treatment facility. And then, similar to Newmarket, we have recommendations in a matrix that we put together. And then at the end, we provided some funding sources for the community to think about on building off this park. So those are some acknowledgements. Those are our contact information, and that's it.
Great. Thank you so much, Kyle and Jane. This has been very educational for me, so thank you. We have a few questions that I've got in the chat. If you have any other questions, please feel free to add those to the chat while we go through these. We are a little bit shorter on time, but really wanted to hear all of that out. So thank you. We're going to start out with some questions on groundwater rise and understanding it. We have a question about the controlling factor in groundwater rise related to sea level rise, and understanding if it's more about distance from coast or elevation above the coast. And I'll send that to Jane first.
Yeah, sure. So basically elevation of the land surface is important from the perspective of impacts. So when you're talking about groundwater rise caused by sea level rise, as you move back from the coast, the effect of sea level rise gets less and less and less. So it is distance from the coast that's causing the effect of sea level rise to be diminished. But the elevation of the land surface is important for the effect. So when you have a land surface that's high relative to the groundwater table, meaning that the groundwater is deep below the land surface, a small amount of groundwater rise isn't going to matter. So the real issues, and this is what Kyle was showing in the last few slides, is the real areas of vulnerability are those areas where the groundwater table is already close to the surface, and then it rises on top of that. And that's where the infrastructure gets impacted. So it's two things. It's distance from the coast and it's elevation of the land surface in terms of impact.
Thank you. And following up, just trying to translate the models that you went through, how might these vary or may need to be adjusted based on the rocky, hilly communities that most of the people in this chat are from? How might the models vary?
Right. Well, I can answer that as well. Ryan might want to jump into. Cape Cod is very different from Maine, very different from New Hampshire. So New Hampshire has a fairly shallow, unconsolidated zone of sand and gravel and silts and clays on top of bedrock, and the bedrock is fractured, much like Ryan was describing for Maine. A lot different from Cape Cod, a lot different from Long Island, where it's a very big, deep glacial outwash aquifer. So when you're looking at a particular community, the geology matters. It really matters. And so that's why we can't take one model and apply it to another area without really modeling that area essentially and looking at the surface water, groundwater interactions and looking at the depth to bedrock and the fracture zones in the bedrock. And fractured bedrock is always difficult to model.
Great. Ryan, did you have anything to add to that? No, okay. Awesome. So now kind of getting into the what can homeowners and what can towns do. We have a question, what can homeowners do if wells are infiltrated with salt water or water quality is degraded? And this is really for anyone.
Kyle, do you want to jump in on that one?
I mean, I can just give a few thoughts. I mean, I mentioned if possible to tie into a municipal system is one. I know that there are expensive treatment options. So reverse osmosis is one of them. Similar to water softeners, there's other options with deionization. But I don't know enough about those other than they're options for homeowners. And I guess the last one, would be potentially if your well is a really deep well. If there's opportunities to go elsewhere on the property to make it more shallow, and you can still draw water from it, that might be potential to help. But this is not necessarily my level of expertise, but those are, I guess, just some options to invest.
I'll throw in a couple ideas too. I think Kyle was right. If you can't attach to a public water system, which is often the case in a lot of coastal areas of Maine, there are not community water systems there. Then you have to look for a different water source. So drilling a secondary well as far from the original well as possible, without getting too far from your home, because that just increases expenses. So try to get a shallower well or far enough away that you're tapping a different fracture. But the fracture geometries are pretty, without doing geophysics or anything fancy, it's pretty much impossible to tell what you're going to get with a new well. So it's a big expense and a big risk that you'll hit the same kind of salt again. There's a couple things you can do to potentially remediate a well that's salty. If you can identify which fracture it's coming from, so you might be able to use like a well packer. It basically seals off the well at different areas to seal off a deeper fracture that has salt. If shallower fractures are better off. And then I want to point out that there's other shallow well technology. So well points, I mentioned in my talk, if you have a sandy or dune area nearby, a well point is an option. And a lot of Maine homes traditionally use dug wells that were dug by hand and lined with stone. And then later they added well tile technology. And these are susceptible to contamination from the surface, so there's downsides. But a shallow well might be a solution, if you can ensure that it's properly constructed and you're not getting contamination from the surface. Shallower wells are much less likely to have salt in them. So that's another option.
I do want to recognize that it is 6:45. I would love to stay on for another 5 to 10 minutes to answer a couple more questions, if that's okay with our presenters. I know it's the evening and people might want to get off. You good? Can we get a thumbs up or a thumbs down? Thank you. Awesome. Thanks. Okay, so circling back to what can I guess we'll ask this one question about homeowners understanding their property. So if someone has a low area on their land that often holds water or remains damp long after a rain, is this indicative of the groundwater level being close to the surface? And I'll let anyone answer that.
In short, yes. I mean, you're seeing the water table is at or above the surface. So a surface water body, a pond or a lake or a stream, is really like an outcrop of the groundwater table. That's how we sometimes describe it, among geologists at least. So yes, it's basically the groundwater table. It might be like a small perched aquifer. So if you have a really clayey soil, there might be shallow groundwater that's there, and then there might be an unsaturated zone below it before you get to the bedrock or in the upper bedrock. But that's not so common. So in short, yes.
So now going outward to what can communities do? There's a specific question about should communities begin to limit the number of wells drilled in a given area? And maybe what might that area look like and how many in an area?
I think this is a really tough question, but it's one I get a lot from communities. And I think Jane and Kyle might have, different answers that really, they vary on the location. It's hard to say, something definitive that can be applied anywhere, like, one well per half acre lot, that kind of a thing. It's just not going to work because it really depends on the geometry and the elevations and the fractures and, everything that's specific to a certain location. But I think in places, so in Maine, the problem is often that there's a huge amount of development pressure right on the immediate coastline, with private homes that are becoming larger and larger and are using more and more water, but are just it's getting denser and there's more homes together. And these are places where there's not public water supply. So every home has its own well. And I think as that density goes up, it is a problem. Wells are interacting with each other, and the increase in pumping rates has the potential to draw in more salt. So I don't have any rules of thumb, but it's something that needs to be looked at when multiple developments are going in close to each other or subdivisions are happening. Those are the kind of situations where a basic model might be in order.
Right, and I just throw in that this is where the modeling actually helps, and a regional model is a good model where a number of communities get together and decide to model the whole area. It's usually better to build a model based on hydrologic boundaries rather than political boundaries of a particular community, and we saw that in New Hampshire. Newmarket wanted it, and then Durham wanted it, and now the whole area wants it. And in retrospect, it probably would have been better from the beginning to find some kind of funding source to just fund a regional model that looks at all of these communities and can identify problem areas for wells and sewage treatment plants and things like that.
So I guess the one thing that I would add in terms of on the regulatory side, we didn't recommend in the Durham project limiting the amount of wells going in, but we did suggest that towns think about if there are wells in some of these areas, that there is something in place for new development. There wasn't anything we really do about existing development, but for new development, that monitoring devices would have to be part of sort of a subdivision plan that was done, and that would require that to show what those levels of chloride are, and if they're above a certain standard, that they would be required to either provide a level of treatment for those homes or be forced to tie into a municipal system if it was available. And so that was on the regulatory side. That's an option for a municipality to take. I think that there probably needs to be a lot more work on that, because it would likely be an overlay district that would be created to regulate that in zoning. But that was one idea that came up, was for new subdivisions and monitoring what the standards or what the chloride levels are now. And if they exceed the EPA standards, then they'd either have to treat it or they would have to tie into it.
And I want to circle back to Jane. You brought up a regional approach, and I know we have some island communities here, and wondering how helpful is it for islands to work together regionally on modeling, and what might this find? And in addition, if taking a regional approach, how regional? What size should we be looking at?
Yeah, so for island communities, it makes sense to do just the island because the natural boundary condition is the tidal water body. So if you were to do a regional study when it's not an island, or when it's a number of communities on a peninsula or communities that are connected, you could do that. But an island would have to stand on its own.
Are there any other questions? Maybe a raise of hand. I'm not seeing anything. So thank you so much. And thank you for staying the 10 minutes over. I really appreciate this. I think it's been really educational and helpful to all of our communities who are working on kind of discovering their priorities and learning more about what they want to take as their next steps. So thank you so much, and everyone have a lovely evening. Bye, everyone.
Thank you.